The northern lights on Jupiter are the most spectacular in our solar system. They're stunning, and they're bigger than our entire planet. They produce incredibly powerful flares that reach terawatts of power. That's more energy than you'd need to briefly supply all of human civilization. What causes them? Why do they seem to pulse like clockwork? To truly unlock Jupiter's mysteries, we needed a way to get closer to it than ever before.
Jupiter is the most extreme environment NASA's ever visited. To send a spacecraft there is a little bit insane. We had to, build an armored tank to go there.
Juno arrived in Jupiter's orbit in 2016. As it got closer, the auroras on Jupiter became so dramatic and active that astronomers said it was like Jupiter was putting on a fireworks display for Juno's arrival, which seems apt given the sheer scale of the spacecraft.
Behind me is the Juno spacecraft, basically life-size. It's an enormous spacecraft, close to 70 feet in diameter as it spins around and cartwheels through space. This is one of the largest spacecraft ever made.
Juno showed us more than we'd ever seen of Jupiter's auroras as they rippled over the planet's poles. The northern lights on Earth are caused by solar winds entering our atmosphere and interacting with the planet's magnetic field. Jupiter's magnetic field, also known as the magnetosphere, is 20,000 times stronger than the one here on Earth.
It extends all the way back to Saturn and perhaps further. And it's the biggest structure in the solar system next to the sun's magnetosphere.
That's one of the reasons Jupiter's auroras are so huge. These gigantic magnetic tentacles capture particles from across the solar system, thrusting them towards the planet's poles, creating this epic light show that never dies. But this is only part of the story. As well as photographing Jupiter's dazzling displays, Juno also began mapping Jupiter's core. And that's when things got interesting. Jupiter is a gas giant. It is full of loads of gas, especially hydrogen and helium. And when hydrogen is under extreme pressure, it acts in a really weird way. It becomes liquid metal. Liquid metal! Like at the core of Jupiter is an ocean of liquid metallic hydrogen. And using some of Juno's findings, physicists in California tried to recreate this extraordinary phenomenon, bubbling away deep inside Jupiter's core.
So basically we are creating a little planet interior inside our laboratory.
Marius Mio and his team at the National Ignition Facility conducted a pretty crazy experiment. They fired lasers at a tiny target, which imitates the core of Jupiter. The lasers simulate the unfathomable pressures going on inside.
So this is the target that we put inside this target chamber. We fill a little portion inside this cone here with liquid hydrogen, about 20 millionth of a gram, and then we shine 80 laser beams from the top and 80 laser beams from the bottom. So the power that we put in the lasers when we shine the laser onto the target is about 500 times the power that is used for the entire United States at a given moment.
5, 4, 3, 2, 1, shot.
Through the laser blast, the team observed this surreal change that takes place in the core of Jupiter.
At this time, the pressure got so high that the light is now reflecting off the shiny surface of the hydrogen. Hydrogen transforms from being transparent to opaque and then becomes a metal, like a shiny metal. If we were to go deep inside Jupiter, we would see a deep ocean of fluid, shiny metal.
And just like that, the planet completely messed with what's possible with the elements. It throws out the rulebook. On Jupiter, this metallic hydrogen makes up to potentially 50% of the planet's mass. And it's this huge liquid metal ocean that accounts for Jupiter's gigantic magnetic field. But that's not all. It also causes charged particles to leak out at its extremities, and it's this that causes the breathtaking auroras that outshine all the others in the solar system. So Jupiter's core is the main source of the auroras, but its moons also wanted to get in on the act, particularly one of the strangest moons in the solar system, Io. This moon is the most volcanically active in the solar system. Its spectacular volcanoes spew plumes up to 300 miles into the atmosphere, adding extra fuel to Jupiter's light show.
So we see Jupiter in the middle, but around Jupiter we see the moons, Io, Europa, Ganymede, Callisto. The gases that come from Io become trapped in the magnetic field, and they become accelerated to very high energies.
These trapped charged particles get dragged towards Jupiter's poles by its all-encompassing magnetosphere.
Energetic charged particles come in, bombard the atmosphere, make it glow. And then we're seeing this glow in the atmosphere of Jupiter.
So the combination of the gigantic magnetosphere, its supercharged liquid metal core, and unique moons create these breathtaking aurorae. But astrophysicists were still puzzled by one thing. Why do these aurorae light up and flash in semi-regular patterns, pulsing in this extremely bizarre way? It took a team at UCL to crack the case. In the time they watched the auroras, they found that they pulsed every 27 minutes. By closely analysing the data sent back from Juno and the European Space Agency telescope XMM Newton, they came to the conclusion that periodic vibrations crashed across the magnetosphere, causing waves of plasma to send heavy ion particles surfing across the magnetic field toward Jupiter. But the mystery isn't over. Just what causes these vibrations? What determines the pattern of these pulses? And why does Jupiter randomly decide on these rhythmic, regular intervals? This is just the beginning of our learning about Jupiter's auroras. And that's just the start of a wider search. There are more like them across the galaxy, waiting to be explored.